So my first derivative is going to be my bottom part unchanged. I'm going to write this with a fractional exponent, just to be careful, times the derivative of my top part, minus my top part unchanged, times the derivative of my bottom part, which is going to give me 1/2 x squared plus 1 to the minus 1/2 using chain rule, times the derivative of the inside, again chain rule, and that's going to give me a 2x all over the bottom squared, which is just going to be x squared plus 1. Alright, that's my first derivative. I can simplify my first derivative out a little bit. This is the square root of x squared plus 1. And I get some nice things to happen. X times x, which is going to give me an x squared. And this x squared is all going to be divided by the square root of x squared plus 1, because this guy up here, convert that, all of this is still over x squared plus 1. I'm going to take this, and I'm going to simplify it just a little bit. I'm going to multiply, on the one hand, I'm going to get an x squared plus 1 all over square root of x squared plus 1. And on the right hand side, I'm not going to have to do anything to make that change. All this is still over x squared plus 1. All I've done is find the common denominator here on the left. So once I've found that common denominator, I'm able to observe that there's some simplification that can happen. On the top I have x squared plus 1 minus x squared all over root x squared plus 1 all over x squared plus 1. These two x squareds cancel each other out, and not only are they going to cancel each other out, but I'm also going to use the laws of dealing with complex fractions and massively improper fractions to take care of getting this to have just one single denominator instead of the two denominators that it currently has. To make that work out well, I'm going to invert and multiply. To make that inversion and multiply happen nicely, I'm going to put this x squared plus 1 in the bottom over 1. When I do that, on the top I'm left with 1 plus x squared plus 1, and again I'm going to write this with a fractional exponent, and I'm going to multiply it by 1 over x squared plus 1. This simplifies to be 1 over x squared plus 1. When I multiply two things that have the same base together, I simply add their exponents. This guy here has a 1/2. This guy's exponent here is a 1, so I get myself a 3/2. So this right here is my first derivative. So I take my first derivative, and I'm interested in finding places where the first derivative is either equal to 0 or it's undefined. Well, this first derivative is never going to be equal to 0, and because this bottom term x squared plus 1 is always going to be positive, this first derivative will never be undefined. So in this case, this time I have no critical numbers. There does not exist any critical numbers. So I'm only going to have my function either increase or decrease. It's never going to have any places where that increase or decrease changes. And that in particular is going to be occurring where this one is always going to be, with my first derivative always being positive, I'm always going to be increasing. Alright, so I know my first derivative. I can calculate my second derivative. To calculate second derivative, I'm going to take a special form of my first derivative. I'm going to do some algebra on it, that first derivative, and I'm going to convert it to be an x squared plus 1 to the 3/2, which is kind of nice. If I can get my second derivative, I'm going to pull that 3/2 down. I'm going to have my x squared plus 1. 3/2 minus 1 gives me 1/2, and I'm going to multiply by 2x on the inside. Just doing some algebra is going to leave me with 3x on top, and on the bottom I'm going to have a x squared plus 1 to the minus 5/2. And once I pulled it down to the bottom of the denominator there, it will suddenly become positive. Alright, that's nice. And with that second derivative, I can talk about critical numbers. Critical numbers relationship in second derivative, which is going to be inflection points. My inflection points for my second derivative are going to come from places where second derivative is 0, or places where my second derivative is undefined. But we don't get any of those here. We're only going to have places where this is 0, and that's going to happen where the minus 3x equals 0, which implies that x equals 0. So this is my one and only inflection point here at 0. I take some test points on either side of it, and I plug those test points back into my second derivative. If I take a test point of something like minus 1 and plug it into my second derivative, well, I'm going to get a positive number on the top of my second derivative, and the bottom part of my second derivative is always positive. This means that I'm going to be concave up. If into my second derivative I plug a test point like positive 1, I'll label these test points just for clarity. Well, on the top I'm going to get a negative number. On the bottom I still get a positive as always here. Overall this leaves me with negative. I'll be concave down. The last thing I'm interested in dealing with here in this guy is going back and taking my original equation and talking about horizontal asymptotes. I think we're probably pretty happy that the limit as x goes off to infinity of this guy is going to be 1. Let's talk about what happens as the limit of x goes off to negative infinity. Well, I take the top, and I'm going to divide everything by x. When I pull that x into the denominator, I have to pull that x into the square root, and dividing by 1 over x on the bottom, pulling that into the square root, gives me an x squared over x squared plus 1 over x squared. Regardless of whether I have positive infinity or negative infinity as my limit of x, the bottom part is going to go to 1. What's going to change and be of interest is what happens in the top of my fraction. What's going to happen in the upstairs of my fraction with this x over x? It's going to be determined by what would happen in my original equation. So let's look very carefully a moment at my very original function. If x is getting negative, this bottom part right here, regardless of what x does, is always going to be a positive number. But if I'm plugging negative numbers in to the top part, this guy doesn't have any squares or absolute values, so he is going to be negative. Which means this infinite limit here, as x is going off to negative infinity, is not going to go to positive 1, but to negative 1. So, to draw my graph, I'm going to have a horizontal asymptote at 1. I'm going to have a horizontal asymptote at negative 1. One of my points is the point 0, 0. This is my inflection point that I discovered up here. To the left of 0, 0, I'm concave up, and I'm increasing. And to the right of it, I'm concave down and still increasing. So this is going to be my final picture of my graph here.